Hi everyone, in this video we're going to be talking about inference about two means, specifically for dependent samples. So we're going to start by talking about testing hypotheses for a population mean from matched pairs data, which is just another way to say that we have dependent samples. So statistical inference methods on matched pairs data use the same methods as inference on a single population mean, except the differences are analyzed. So we've done hypothesis testing on single population means, so this is going to seem familiar in a way for some of the processes. So to test hypotheses regarding the mean difference of data obtained from a dependent sample, which is just matched pairs data, we are going to have some steps given that the following are true. So the sample is obtained using simple random sampling, or the data results from a matched pairs design experiment. The sample data are dependent. The difference are normally distributed with no outliers, or the sample size is large, so we'll say 30 or more. And then the sampled values are independent, and you can check that if the sample size is no more than 5% of the population. So if all of those are true, then our steps are, step 1, determine our null and alternative hypotheses. And so our null hypothesis in each of our tests, two-tailed, left-tailed, and right-tailed, is that mu sub d, which is going to be the population mean difference of the matched paired data, is 0. And then the alternative hypothesis is that mu sub d is just different from the null hypothesis for two-tailed. Left-tailed, it's less than 0. And right-tailed it's greater than 0. And then step 2 is select our level of significance alpha. Step 3, so this is where we split between approaches. For the classical approach, we compute our test statistic T naught, and T naught is calculated as D bar. So D bar is the mean of our difference data, and then minus 0 over S sub d, which is our standard deviation of the difference data, over square root of n. And then we use our t distribution table to determine our critical values. So remember, for your two-tailed test, you have 2 critical values, and you have to divide alpha by 2. And then your left-tailed test, you just have alpha, so negative t sub alpha, right-tailed test, t sub alpha. And you find your corresponding critical value from your table. And then you compare your critical value to your test statistic to decide if you're going to reject the null hypothesis. And then step 5 is to state the conclusion. And then so starting over at step 3, if we use our p-value approach, we still compute our test statistic T naught. We have to identify the degrees of freedom. It's always our sample size minus 1. And then we go to our t distribution table, but we're looking for p-value this time. And remember, with our two-tailed test, the p-value is twice the probability that t is greater than our test statistic. And then we could also use technology instead of the table to get our p-value. And then step 4, just compare our p-value to alpha to decide if we're going to reject the null hypothesis. And then last, state our conclusion. So these procedures are considered robust, which means that minor departures from normality will not adversely affect the results. However, if the data actually has outliers, we shouldn't use the procedure. So just something to keep in mind. So let's take a look at this example. Professor Andy Neal measured the time in seconds required to catch a falling meter stick for 12 randomly selected students' dominant hand and non-dominant hand. The professor wants to know if the reaction time in an individual's dominant hand is less than the reaction time of his or her non-dominant hand. A coin flip is used to determine whether reaction time is measured using the dominant hand or non-dominant hand first. We're going to use alpha equals 0.05 for our level of significance, and then the data for this experiment is here. So we had 12 students, and then our dominant hand and non-dominant hand. And these are the time in seconds to catch the falling stick. Okay, so we want to compute the differences for each of our variable values. And so we're going to do it as the time of the dominant hand for the ith student. So that would be the first, second, third, and so on. And then that minus the time of the non-dominant hand for the same student. And we're expecting the differences to be negative because we can assume that the dominant hand, the reaction time is quicker. So we want to determine if mu sub d is less than 0. Okay, so here we have an added column to our table where we have those differences in time depending on the hand. Okay, so now if we just compute the mean and standard deviation for those differences, we're going to get that d bar is negative 0.0132, and the standard deviation, S sub d, is 0.0164, and we just rounded those values. And then we first of all want to verify that our data comes from a population that is approximately normal with no outliers. So remember how to do this. We make a normal probability plot and a box plot. Okay, so I'll show you how to do this real quick on StatCrunch, but we've done this in the past. So here's our normal probability plot and our box plot, and we're just looking here for any outliers, and here we want to calculate the correlation coefficient, and we compare that to our critical value, and if it's greater than, which in this case it is, we can say our population is normally distributed. Okay, so let's head over to StatCrunch real quick and just create these graphs. So I've inputted our difference values here in StatCrunch, and I'm going to go ahead and go to Graph, and first down to QQ Plot, and select my column. I want to calculate the correlation statistic. Let's go ahead and add normal quantiles, and just hit Compute, and here we have it. So there's our normal probability plot. And notice our correlation coefficient value 0.98. And so then to get our box plot, we're going to go back to Graph, Box Plot, select our column, and let's go ahead and draw our boxes horizontally, and there's our box plot with no outliers. All right, so now let's just go quickly to our critical value table to compare this value of 0.98. So if we go down to sample size of 12, which we're working with, the critical value is 0.928, and our correlation value was greater than that, so that's why we can say that our data is approximately normal. Okay, so now we can move on to our first step and determine that our null hypothesis is that mu sub d equals 0 seconds, and on our alternative hypothesis is that we want to know if the reaction time is less. So technically the dominant hand is less reaction time than the non-dominant hand, so mu sub d is less than 0, because remember that's the difference. So it was the dominant time minus the non-dominant time, so if it's negative, it would imply that the dominant hand time was faster. Okay, so this is a left-tailed test based on that alternative hypothesis. Our level of significance was given as 0.05, and then we're going to do the classical approach first. We have our sample mean and standard deviation, and then we plug those into our test statistic formula. So T naught, plugging in our values, is negative 2.788. And now because it's a left-tailed test, we're going to determine our critical value based on our alpha of 0.05, level of significance, our sample size minus 1, that's our degrees of freedom. And so I'll go to the table real quick and show you that this is going to be negative 1.796. So on our t-distribution table here, we're going to go down to 11 degrees of freedom, and we want alpha to be 0.5, which is here. And so we have 1.796, but if we put a minus sign, that's why we got negative 1.796. So then we analyze this, comparing it to our critical value to our test statistic. And because our test statistic is less than our critical value or lies within the critical region, we reject the null hypothesis. So we can conclude that the sample data provides sufficient evidence at the 0.05 level of significance to conclude that the reaction time in the dominant hand is less than the reaction time in the non-dominant hand. So we'll do this one again using our p-value approach. And we still have d bar and S sub d. Our test statistic value is still negative 2.788. And now, because we are doing the left-tailed test, our p-value is the probability that t is less than our test statistic, okay, with 11 degrees of freedom. Now, because of symmetry, we can say that the area under the curve to the left of our negative value, negative 2.788, is actually equal to the area under the curve right of positive 2.788. And why we care to even do this is because the table gives us the area to the right. And so we're going to say that the probability that t is greater than positive 2.788. Okay, so we'll go over to our table and find our row corresponding to our degrees of freedom. And we're going to look for where 2.788 is closest in value and its corresponding areas. Okay, so 11 degrees of freedom is this row. And notice 2.788 would be in between these two values. So going up, that's going to be area between 0.005 and 0.01. Okay, so now we know that our p-value is between 0.005 and 0.01. And so to get a more accurate value, instead of just a range, we can use StatCrunch. So let me take you over there to show you that the p-value is 0.009. Alright, so in my table I did go ahead and add the times for the non-dominant hand and then the times for the dominant and non-dominant hands. And so with those inputted, I can go to stat, I'm going to go down to t-stats, and we're going to go to paired. So I'm going to select my dominant hand and then my non-dominant hand for my columns. We've already computed the differences, but if I hadn't, I can click on that. And our alternative hypothesis is that mu sub d is less than 0. So let me put that in there. And then we compute. And here we have it. And so notice our p-value is 0.009. So our p-value of 0.009 means that if the null hypothesis is true, we expect the sample mean of negative 0.0132 of a second or lower in about 9 out of 1,000 repetitions of this experiment. The results we obtained are not consistent with the assumption the mean difference in reaction time between the dominant and non-dominant hand is 0 seconds. So another way to say this, because the p-value is less than the level of significance, 0.009 was less than 0.05, then the professor rejects the null hypothesis. And then we can conclude, just as before, the sample data provides sufficient evidence at this level of significance to conclude that the reaction time in the dominant hand is less than the reaction time of the non-dominant hand. So then our next objective is to construct and interpret confidence intervals for the population mean difference of matched pairs data. So our confidence interval has a lower bound and an upper bound, and then notice it's just our mean, d bar, of our difference, and then minus for the lower bound, plus for the upper bound of our critical value at our alpha level of significance times our standard deviation. And then note, the interval is exact when the population is normally distributed and approximately correct for non-normal populations, provided that n is a large sample size number. Okay, so let's try this example. Same situation. We have our data from our dominant and non-dominant experiment dropping the stick. We're going to estimate a 95% confidence interval estimate of the mean difference, mu sub d. Okay, so by hand we'll compute the differenced data and verified that they come from the population that is approximately normally distributed with no outliers. We did all that previously, so we don't have to do that again. And our sample difference, we computed that d bar, and our standard deviation, we also computed that. Okay, so then we go to our t-distribution table with alpha at 0.05, 11 degrees of freedom, and what we want this time is we want t sub alpha over 2. So from that table you would look for t sub 0.25, and we're going to get 2.201, and then we'll plug into our formulas for upper and lower bounds all of our values that we have. So we have our d bar, our critical value, standard deviation, and we get our lower bound is negative 0.0236, and our upper bound is negative 0.0028. And so we can say we are 95% confident the mean difference between the dominant hand's reaction time and the non-dominant hand's reaction time is between negative 0.0236 and negative
0.0028 seconds. In other words, we could say that we're 95% confident the dominant hand has a mean reaction time that is somewhere between 0.0028 and 0.0236 seconds faster than the non-dominant hand. Because the confidence interval does not contain zero, the evidence suggests the reaction time of a person's dominant hand is different from the reaction time of the non-dominant hand. So then we can do technology, and we did most of the work in the previous example for step 1, and then we can use something like StatCrunch and get our lower and upper limits. So let me take you over there real quick and show you how to do that. Alright, so since we've already computed all these things in StatCrunch, what I can actually do is, if I cleared this already, I could follow my previous steps, but I'm just going to say edit this, and all I really need to do here is change this to a confidence interval. We wanted a 95% confidence interval, so that's what I'm going to keep, and hit compute, and then there's my lower bound and my upper bound. And so then we can say the same things. We're 95% confident the mean difference between the dominant hand's reaction time and the non-dominant hand reaction time is between our lower limit and our upper limit. Okay, so that's it for this one. Thanks for watching.